This is sample problem 2.03 from the Walker textbook, and we're going to practice differentiating the position function to find the velocity function and acceleration function first. So here we have a polynomial, so we're going to use the power rule to find velocity with respect to time. So we'll take the first derivative and find velocity. So if I take the first term here, 4 is really 4 times t to the 0, or 4 times t to the 0 power. So that completely goes away. The next term, I take the exponent, which is 1, so 27t to the 1. So I bring the 1 down. 1 times 27, or really negative 27, is negative 27. And then I decrement the exponent, or I take the exponent and subtract 1 from it. Well, t to the 1 minus 0, or sorry, 1 minus 1 is 0. So the new exponent is 0. T to the 0 is just 1. So now I just have negative 27 there. Next term, I bring the 3 down as a coefficient. So I have 3 as the coefficient. And then t is now to the 3 minus 1, or second power. Okay, and then the acceleration function, I do that again. I take the derivative of the velocity function to find the acceleration function. So I've got the negative 27 goes away completely. That's a constant. So if I have a constant, then the exponent of t is 0. And when I multiply that down as a coefficient, I take 0 times negative 27 and I just get 0. Okay, and then when I multiply 2 times positive 3, I get my coefficient here is 6, and then I have t to the first power, or just t. Okay, so now I have my two functions, and I already graphed them. I just had wanted to display these for us to show each function. So just to make these a bit bigger, this is x as a function of time, and then I had graphed this is velocity as a function of time. And if I scroll down, you can see the linear function here for acceleration as a function of time. So what I wanted to point out here that doesn't seem to be mentioned in the book is that when velocity, when the object has a maximum position or a minimum position, right? Then it's got a velocity of 0, okay? So in time here, if I kind of bring like a dotted line down, oops, in time, notice that coincides with the times that the velocity is 0. Oh, that doesn't look quite right. It looks like when I size these graphs, or maybe I just can't draw a straight line. But though that's not a coincidence, okay? Because when an object is turning around like that, it must stop to turn around. So if you are asked for a maximum or a minimum on the position time graph, one way to find that is actually to use the velocity function and solve for when the velocity function is equal to 0. Or you know, if you're asked for when does the velocity graph have a maximum or a minimum? Hey, look at that. Well, here's the minimum of the velocity function. That's when the acceleration graph is equal to 0, right? So you're going to need that when you solve for homework. But this particular problem isn't asking for that. It's just asking when and where does the particle stop? Well, first let's solve for when. Let's solve for when does the particle stop. In other words, I'm looking for a time when the velocity is equal to 0 meters per second, okay? So let's solve for that. Okay, so then I'm just gonna set, you know, move 27 over, and then I'm gonna solve that, and I find that time is equal to 3 seconds, you know, and I'm getting, well, sorry, plus or minus 3 seconds technically, which you can see on the graph if you look really carefully. In physics, we're focusing on positive time. And so we've got the when is 3 seconds. So I'm just going to box that and assume it's positive. But where is the particle when it stops? Well, then I'll go back and plug in 3 for time back into the position function. Let me give myself a little more space here. So let's do that. So then I'm just solving for x at 3 seconds using the original function that the problem gave me. Okay. So when I solve that out, I get -50, which I think this problem had given us, I think, meters as our units. So that corresponds to this spot right here, which is a minimum at this moment when the particle stopped. Okay, I've got to stop right there. We could use the graphs to describe the rest of the problem where we're describing the motion and how it moves from, in positive time, we'd probably start right here on the graph and describe how it moves in the negative direction, slowing down, and then stopping for a split second, and then speeding up, going in the positive direction.